For lesson 30, we are going to be making graphs, and deciding if they represent functions. We're also going to be taking a little bit deeper look into the concepts of domain and range as they relate to graphs. All right? So we're going to be spending a little extra time there. This is going to be a good lesson to take good notes and keep good focus on. Because if you decide to take time to play and show your neighbor what you sketched on your paper, it's not going to be a great idea for you to do that during this lesson today. Nick and Sean, don't let him distract you, man. You're better than that. Seriously, A game today. A game today or you'll be lost. And this is a little bit out of the ordinary. Usually the later Saxon lessons right before the unit test are a little bit easier. That's not true for this one. This one's going to be a little bit more difficult. It is tested. The test is when? Tuesday. All right. So, a linear equation. This is some review stuff. I don't think you need to write this down necessarily. A linear equation is an equation whose graph is a line, right? Duh. Linear is linear, right? Linear equation. You can use a table of ordered pairs to graph the relation represented by any equation, right? One of the things that we're going to be doing today is using a table of values, creating a table of values to graph the relation represented by all different types of equations. Equations that you've never worked with before. Y equals the absolute value of x, for example. You've never graphed that or worked with the graph of that. But we're going to make a table of values to determine what that graph looks like. Okay? You can do that with anything. To determine if the graph represents a function, we can use the vertical line test. If the vertical line intersects the graph in more than one place, it is not a function, right? Because that shows that we have two x value or one x value that is shared with two different y values. So just some review stuff, all right? A linear function is a function whose graph is a line, and every linear function can be written in the form f of x equals mx plus b. Now, if I'm using f of x, this is function notation, right? And what did the f of x replace? Y equals mx plus b. So this is the same as y equals mx plus b. This is the good old slope-intercept form equation of a line. We're going to wear it out soon and very soon. You're going to learn another equation of a line that you've never seen before called the point-slope formula in Unit 6, Unit 5. Okay, so we'll use these things for different things. Where m and b are real numbers, that's important because we're graphing in the real plane and not the imaginary plane. The xy plane is the real plane. Okay? All right. So, here we go. Here's the task at hand. Graph the equation using a table of values and decide whether the graph represents a function, whether it is linear or nonlinear. Now, can we answer any of these questions before we graph it?
Yeah.
Which questions can we answer with certainty? Elizabeth?
If it's like a linear equation.
If it's linear, right? Is it linear? Yes, absolutely. Y equals mx plus b. M is 2, b is 5, right? What else can we ascertain?
Is that a function?
It is a function, right? Because all lines are functions except vertical lines, because vertical lines fail the vertical line test, right? Vertical lines by definition are not functions. And vertical lines cannot be written in y equals mx plus b form either, because there is no y in a vertical line. Okay? All right, so how would we do this if we're graphing y equals 2x plus 5 by making a table? So you guys take a second and draw you don't have to be real detailed. I do expect you to do all of this today. Don't just sit and watch. Engage your body. Put your mind in gear by moving that hand. So y equals 2x plus 5, we're going to make a table of values. That means we're going to pick some x values and we're going to plug them in and find the y values that relate to it. You don't have to have a whole lot of detail, Nick. Don't do that. Don't spend time doing this kind of detail. What I want you to have is an x-axis and a y-axis. That's it. That's good enough for me. All right, we'll go from there. We'll put the detail. We'll let the numbers that we get from our table dictate what we put on the graph. Okay? All right, so it's always a good idea to pick some negative values, pick some positive values, so we got a good representation of numbers. Always use 0, because 0 is easy to work with. It's easy to add, it's easy to multiply, it's easy to square, it's easy to take the square root of, it's easy to take that. It's easy to do anything with, right? So let's take a negative value. Let's use negative 2. Let's use negative 2. Let's use 0. And let's use 1 and 2. How many points do you have to draw a line? 2 points. You have to have 2 points, right? Right. If we're just doing points, we need 2 points to make a line. So it's a good idea to do 3 points in this scenario, just in case you made a mistake on those other 2 points, right? One of the other 2 points, or both of those, you'd have to make the same mistake 3 times to get 3 mistakes that line up. So, if your points didn't line up, then you'd know you made a mistake. All right, so let's evaluate. What's 2 times negative 2 plus 5? 2 times negative 2 plus 5 is 1. 2 times 0 plus 5 is 5. 2 times 1 plus 5 is 7. 2 times 2 plus 5 is 9. Now, we're not going to make a whole lot of it at this point, but what's the change in each of these? 2. What's the change in this one? 4, but this side changed by 2. So if this changes by 1, the other side is changing by 2. If it changes by 2, the other side is changing by 4. So there is a relationship that we're going to talk about at some point, and that is directly related to the rate of change, which is the slope of the line. If you increase x by 1, you're going to increase y by 2 because you're multiplying x by 2. Okay, so we've got these 4 points. Negative 2, positive 1 is right in this vicinity, right there. And I'm doing this because this doesn't like to make dots for some reason. It wants to select it. 0, 5 is there. 1, 7 is there. And I'm not going to do 2, 9 because it's not on the grid. All right, so this line goes through those points and looks like that. Whenever you're graphing a line for me, I do want you to use a straight edge, so it's nice and straight. Okay, now that could be the corner of a notebook or a piece of an index card. It doesn't have to be a ruler of sorts. You're going to go from there. Okay? All right, any questions about what we just did? Is this unfamiliar to you? Have y'all done this before? You've done this before. Okay, Griff, you've done this before? But you get it, right? Okay, I knew you would. Griffin's smarter than the average bear.
Griffin's smarter.
All right, y equals negative 3x plus 2. Let's have a look at this one. Y equals negative 3x plus 2. And let's graph it by making a table of values. Now, we already know it's linear, right, because it's in y equals mx plus b form. We already know it's a function because it's not a vertical line. All right? Vertical lines don't have a slope. This one has a slope of negative 3. Okay. Any slanted line is a function. And this one is slanted. The slope's negative 3. It's going to run downhill. All right? All right? Horizontal lines are functions, yes. Okay? X and Y table.
Negative 2.
Let's don't do negative 2. Let's use negative 1, 0, and 1. Let's just use 3 points here. Now, it might be helpful, guys, to always use the same increment. I know we switched up a little bit last time, but if you use the same increment with your x values, you'll see a pattern on the right with your y values. So you could examine the pattern, just the pattern, and know that you're off. All right, so this time, every time x increases by 1, we're expecting y to do what? Decrease by 3. That's what it should do, because the slope, the rate of change, is negative 3. What is y doing? Well, it's negative 3 times whatever x does plus 2. It's negative 3 times whatever x does, and if we increase x by 1, we're going to subtract 3 from y. All right, so if we put negative 1 in, what do we get? Negative 3 times negative 1 is positive 3 plus 2, which is 5. If we plug 0 in for x, we get 0 plus 2, which is 2. Negative 3 times 1, negative 1. And again, because my increments here on this side are all plus 1, what am I doing on this side every time? Minus 3, minus 3, right? And that pattern is always going to be consistent if we have a linear function. All right? Is that clear?
Yes, sir.
Now, you may or may not have been pointed that fact out before. I'm guessing not, but that's the case. All right? It's not really something you do. All right, so let's graph these. Negative 1, 5 is up here. 0, 2, right here. 1, negative 1 is right here. It's a nice straight line through those 3 points, but that's not a nice straight line. And sometimes this is a little bit harder to do than you might think. So something like that.
It's around there.
Now this line's different from the previous line, right? Describe the difference in these two lines. Those of you who have some notes that you can use.
One's going downhill, one's going uphill.
One's going downhill. Which one's downhill?
The second one's
This one is downhill, right? He's got a picture of the little guy on his bicycle going left to right. He'd be really going downhill. This was a pretty steep line, right? This line is steeper than the other line. Would y'all agree with that? What was the slope of the other one? 2, right? It was uphill. Positive slopes go uphill, negative slopes go downhill. So there's a lot of things that we could look at with these lines as we go through, but we're on the first example. All right, now this is different. This says graph the equation using a table of values. Okay, we can do that. Decide whether the graph represents a function and whether it is linear or nonlinear. Now, what do you think?
Non-linear.
Why is it nonlinear?
Because 6 times 6 is 36, but so is negative 6 times negative 6. It's also 36.
That is brilliant, right? So unless it's a horizontal line, we got problems, don't we? Because negative 6, 36, and 6, 36 are linear. We could draw a line through those two, but it's not. This is not a horizontal line. How do we know it's not a line? Is it written in y equals m times x plus b? No, it's not in linear form. This is a second degree. Y'all listen to me. This is a second degree function. Second degree functions are called quadratic functions. Now we're getting into some higher math here, right? Higher degree things. This is a higher degree equation. We've not worked much, any with higher degree equations up to this point. But let's make a table of values to graph y equals x squared. Table of values. Now, like I said before, it's always going to be very, very helpful if we choose some negative values and some positive values. Because we're squaring it, we don't want to get too large of numbers. But also, listen carefully, the higher the degree of the function is, the more points we need to determine its shape. First degree equations, it only takes two points to determine its shape. With higher degree functions, it takes more points to determine the shape of the graph. So as a general rule, we use 3 for first degree. Let's use at least 4, preferably 5 for a second degree function. So let's start with negative 2. Negative 1, 0, 1, and 2. Keep our numbers nice and small because we're squaring them. And 3 squared is 9, 4 squared is 16. We don't want to get off the graph, work ourselves too hard. And why are we getting to choose these values?
Because it's a variable.
It's a what kind of variable? X is the
Dependent.
independent variable. It's free, right? We can choose values for X to determine what the value of Y is. All right, so if we square negative 2, what do we get? 4. If we square negative 1, we get positive 1. If we square 0, we get 0. If we square 1, we get 1. If we square 2, we get 4. So now I've got all these points that I can graph. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1. Ooh. And 2, 4. Alright, so I'm going to do my best here. This looks something like this. 3 and negative 3 would be 9, right? 3 squared is 9. Negative 3 squared is also 9. So, well, you know, our graph's going to look something like that. Now, we have graphically confirmed that this is not linear. Right? Is it a function?
Yes.
Why is it a function?
Because even though it's not, it passes the vertical line test.
Passes a vertical line test, right? All right. Let's talk a little bit. Just talk a little bit about what the domain of this function is. Right? Now, this is getting into that more difficult concept. What is the domain of this function? Why is it all real numbers, Josh? Because it goes from side to side. It continues to open out, right? Can we square 7? Can we square 7,000? Can we square 7 million?
Why not?
So x goes forever in this direction. And can we square negative 7 million? Yes. We can square any x value. Now, so the domain is all real numbers, and we can write that like this. Okay, what is the range of this function? Now, range relates to which variable? Y. What y values does this function take? Can't be anything, can it? It's got to be what?
Positive. I was gonna say
Positive or
positive.
it can be
0.
0. Obviously, it can be 0, right?
Yeah.
Not whole numbers. Not whole numbers. We're talking about positive, or here's the exact word, non-negative real numbers. And we would express that like this. Y has to be greater than or equal to 0. Right? Because what does y do? What does this function do? It starts at 0 and it goes to the moon.
It's a ray.
Okay?
Goes from here.
Good? Now, we're doing a graphical analysis of domain and range. This is tough. This gets difficult for students. I promise it is. It's tough for seniors, calculus students. This concept of domain and range is tough. It's not for me, so it's a little bit difficult sometimes to teach. I just want to say, what do you mean you can't understand it? It's right there. You see it? All right? So we'll talk about that more as we move through this. Now, who thinks they can match Table 1 to the appropriate graph? Just based on what we've done so far, Table 1 goes to which graph? Raise your hand and let me know here. Jay, which one do you think it goes to?
Table 2.
No, Table 1 goes to which graph? Griffin? Graph 3 is correct. And the reason being, Griff, what's your justification for that?
Because 0 equals 4.
Yeah, you could take 1 point, right? This is the only graph that goes through the point 0, 4. That's the y-intercept, by the way, where x equals 0 is the y-intercept for the graph. All right, what about Table 2? Which graph does Table 2 match, Bo?
Graph 1,
Graph 1 is correct. And you use what logic?
origin and the y-intercept.
Yeah, the y-intercept's -1, right? And then, of course, then Table 3 would do this. What are some other things we could use to, what makes Table 3 go to Graph 2 automatically? The slope is negative. It goes downhill, right? So we can see right off the bat, if we're just talking about slope, okay, this slope is positive. This slope is negative. This slope is positive. Which one of these is the steepest? Graph 1 is the steepest. 5 is the steepest slope. All right, so you see, the more tools you have, there's literally dozens of ways that you could identify these graphs based on the equations without even looking at the tables. Okay? We're getting tools. All right? Tools that we can use for lots of stuff. All right? Let's try another one here. This one is going to require a little bit more thinking. All right? Let's see. Teeter. See if you can do this one. Which one would this be?
Hang on, this is gonna take me a minute.
That's okay. That's all right. Everybody be thinking about it. Which one is it and why?
What about why?
Is it two?
It is graph 2. Why? How did you come up with that?
This slope is one.
Yeah, it's a linear, right? Y equals mx plus b. Y equals x plus 3. This is a linear equation, which means its graph is a line. And we've only got one line there. Now, the other two may be a little bit trickier. Griffin, what do you think? Which one can you identify?
Equation B is graph 3 because it has to be a positive.
Equation B is graph 3 because what does that absolute value do to things? Makes it positive, so it's going to flip any negative number up, right? This looks linear, doesn't it? It almost looks linear. Y equals x plus 3, but it's not x plus 3, it's the absolute value of x plus 3. So look at the relationship between these two graphs. This one takes the negative parts
There you go.
and flips it right up. That's exactly what it does.
So would that be a right?
Okay. Yes, it would actually be a right angle. Not always. Absolute value, if it had like the absolute value of 1/2 x, and
Because
Um,
it's one side.
yes. All right, slope is 1 on one side, slope's -1 on the other side. So yes, that's good logic. Well, that kind of eliminates, by process of elimination, now we're getting to see what the square root of x plus 3 looks like. It looks like that. Now, why does this graph just kind of stop? Y'all see what I'm talking about by stop? Now, it's going from that, but it kind of, if we look to retrace it back this way, it goes to right there and stops. Why does it stop right there?
Because
What about it, Carson?
I thought I had the answer, but well, because
Abby?
can't you not take the square root of a negative
You
number?
can't take the square root of a negative number, right? So y equals the square root of x. We can't put negative numbers in there, so it stops or starts at x equals 0. Yes, right? Is everybody clear with that? Jay, sit down, bub. Come on. Nice timing. It starts at x equals 0. We can't take the square root of a negative number, right? Is everybody clear on that? So, let's talk about this graph. One at a time, let's talk about these graphs. This one right here, what is its domain? What's the domain of that graph?
all numbers.
And zero.
X, positive numbers and zeros. How do we write that? X has to be greater than or equal to 0. Yes, very good. What's the range of that first graph? Which is this equation, right? Y has to be, it's going up. Where does Y start? When X is 0, Y is 3. So Y is greater than or equal to 3 is the range. And it's going to go up forever. And those of you who are daydreaming are not going to get this. Focus. Strain. All right? Let's talk about the domain and range of graph 2. What's its domain? X can be anything, right? And Y is going up forever and down forever, so it can also be anything. Right? Y is going to go up forever, down forever. Okay. All right. What about the final graph? Let's talk about the domain and range of graph 3. What's the domain of graph 3? Can x not be anything?
No.
X can be anything. We can take the absolute value of positive numbers. We can take the absolute value of 0. We can take the absolute value of negative numbers. Not a problem. Domain is everything. Range for this particular graph looks like it starts where? Y starts at 3 and gets bigger. So Y is greater than or equal to 3. Excellent. Okay. Excellent. So that's questions of domain and range based on graph. You've had 1 or 2 questions in your textbook on this subject. I think they were a little premature. We hadn't really talked about it yet. Okay, but we have now. All right. Then the test questions that you'll have will be pretty straightforward on this. Now this says use the graph to identify the domain and range. We just practiced that quite a bit with those previous problems. What is the domain of this function? No, domain is always related to x.
X is 0.
Greater than or equal to 0. Why does it have to be greater than or equal to 0? Because you can't take the square root of a negative number, right? Not in the real number system, okay? What's the range?
Y is greater than or equal to 1.
Y is greater than or equal to 1 is correct. Because it starts right there at 0, 1 and goes up. It's going to go up forever. Because the square root of 9 million is 3,000. It's going to get higher. It's growing slowly, but it's growing. All right? Good. You guys got that pretty good. Use the graph to identify the domain and range. What would the domain of this one be? All real numbers. Is there any x value that we can't square? Okay, so the domain is all real numbers. What's the range? Y is greater than or equal to -2. Very good. Very good. Okay. Last problem. Football team raises money by washing cars. They charge $5 per car and spend a total of $4 on soap. The table shows the money they raise. Make a graph and use it to find the amount they raised by washing 7 cars. Write the rule in function notation. So let's talk a little bit about let's don't make a graph. All right. Let's figure out what it would be for 7 cars. Because we can see the change, can't we?
Yes, sir.
As x is increasing by 1, what's happening to y? It's increasing by 5. So the rule is, the rule is x increases by 1, y is increasing by 5. So the next y value would be 26, and the next y value would be 31. So you need to learn to examine tables like that, right? So, what's the equation that is represented by this? The slope is what? Yes. Slope is 5. So if we're doing function notation, y equals mx plus b, f of x equals 5x minus 4. That's it. Okay? This is a function, right? F of x equals 5x minus 4. Does everybody see where that came from? Because we know the slope is 5, and we know that the y-intercept is -4. Where x equals 0, that's the y-intercept. So b is -4. Zeros are very important. All right? Excellent. Excellent job today. So write this down. Is this the same as the syllabus?
No.
I feel like I changed
It's
this.
not.
It is A through G, and I don't think it's 19 through 29. So disregard this and look at the syllabus.